Welcome back for the second part of this lecture, where we will focus on the classification using instance-based learning, and more specifically with the k-nearest neighbor algorithm. The concept behind instance-based learning is that we will use instances, so samples that are in a training dataset, in order to make inference on a query sample, typically a sample on which we want to know if it's, for instance, a given task, a given class or another one. And in order to illustrate a little bit the concept behind instance-based learning, we have this funny cartoon that shows how we can be, even us human, very deeply influenced by the opinion of our close relative or close friends. And here with the k-nearest neighbor algorithm, it's literally the same concept. We'll try to find in the dataset the close samples, so the samples that are very similar to the ones that we would like to classify, and we will use those set of very close and similar or near solution or samples in order to make the inference. And so before talking about the k-nearest neighbor algorithm, let's start with the one nearest neighbor algorithm, so the nearest neighbor algorithm. And so as I said, it's a classification algorithm first, so we will have to try to find, typically if we have a query sample like this blue cross, we will need to know if it's part of the red dot class or if it's part of the green square class. And so in order to do this, the one nearest neighbor algorithm will try to find which sample from the training dataset. So here the training dataset is all the samples that are shown on the screen, that is composed of the red dots and the green squares that you can see here. And so after finding the nearest neighbor in the dataset, the outcome of the algorithm will just assign to this query sample, so the blue cross, the class label of the nearest neighbor sample. So in this case, it will assign to the sample the class of the red dot, because the nearest sample is a red dot. There are some important aspects with the nearest neighbor algorithm, and that actually part also of the k-nearest neighbor algorithm. It is that it's a non-parametric model, and that's quite important because this means that the decision boundaries that is formed by the algorithm is actually not predefined. It's not something that we impose to the model, but instead something that naturally emerges from the dataset and from the samples we send it. And the question now is, what will be the problem of using just the nearest neighbor solution, and why not more than just one solution? And here you can easily have a feeling about this, because you can easily see that the solution actually, the red point or the red dot here, might be just one sample that is a bit lost in this bigger pack of green squares. And what is interesting is that it's very likely that it's just noisy samples. And so here, intuitively, if we had to make a decision, we will rather say that the blue cross is rather a green square compared and not a red one in general. So that's why there is the k-nearest neighbor algorithm. The idea is that instead of just using one solution, which might be sensitive to noise, typically if we have an outliers, and which can also overfit to the data. So we will talk a little bit about overfitting in the last part of this lecture, but you will also cover this more in depth next week with Marek lectures. And the idea is that instead of using just one sample that can be quite sensitive to noise, we can use the k-nearest neighbors. And so here in this case, instead of just selecting or considering the red dots as before, we will actually consider, in this case, 5 samples around, the 5 nearest samples. And here, as you can see, we now have one red dot, but on the other hand, we have 4 green squares. And here, the outcome of the algorithm will simply be the class with the largest number of samples in the k-nearest neighbors. So here in this case, the winning class will be the green squares, because we have 4 samples compared to just one sample for the red dots. And it's also quite important to select a k value that is an odd number, because by doing this we ensure that at the final stage for the vote we will always have a non-even distribution of votes, but we will always have a winner in the decision task. But then the question is how we can actually select the value of the k parameters. And the idea is that if you increase the k value, it will make the classifier have a smoother decision boundary. So for instance, here you can see that we have boundaries that change for every single sample that is a bit different. We even have like small island in the middle here. So that's why that's what we call a non-smooth solution. While on the other end, with a larger k value, we have something that is way smoother, just moving a little bit around and actually ignoring some solution like here a couple of blue dots and here a couple of red dots as well. Another effect of increasing the k value is that it's actually making the decision boundaries less sensitive to training data. As I said, if we have some samples that are a little bit outliers or not explained by the major tendency, we will actually ignore them. So in practice, what this means, if you remember last week's lectures, it will lower the variance of the decision, while for the smoothness of the boundaries, on the other end, increasing the bias. And so the question is how we can choose the perfect value for the k parameters. And the issue is that this is most of the time questions that is very, or the answer will be very task or dataset specific. This means that for every single dataset, you will need to probably find a different value for k. And in order to do this in a more or less automatic manner, we usually use a validation or cross-validation procedure, typically using validation dataset, and you will learn more about this in the next lecture about evaluating different algorithms and making sure that the decision of the k value is the most appropriate for your task. Then, when we talk about k nearest neighbor, we naturally talk about a neighborhood, and so on. So this means that we need to define a distance metric or metric space. And there are a lot of different variants or different existing distances that can be used in the k nearest neighbor algorithm. So for instance, we have the Manhattan distance, which is the L1 norm. If you don't know why it is called the Manhattan distance, you can easily visualize this by thinking about the layout of Manhattan, which use a very orthogonal layout of the street with the avenue in one axis and the street on the orthogonal axis, and you have a lot of blocks of houses, and you can easily imagine that if you have to count how much you need to walk to go from point A to point B, you will literally count the number of sides of building blocks you will actually have to walk through. And that's why, and unfortunately, you cannot go across buildings, you cannot traverse the building. So you have to walk on both edges of the squares, and you cannot actually use a diagonal like in the L2 norm. So that's why it's called the Manhattan distance. It's because it's a good representation of how much you need to walk or to drive if you want to go from point A to point B in Manhattan. Another example of distance, as I said, is usual one. It's the Euclidean distance, the L2 norm, that is computing the Euclidean distance between two points. But other alternatives exist. So typically we have the L infinite norms, the Chebyshev distance, and you have also more specific distances like the Malanobis distance if you have a non-isotropic distance space, typically when it's related to Gaussian distributions. That's typically a distance we might use in the unsupervised density estimation techniques in the future lectures. There are also the Amin distances if you have binary strings and a lot of other techniques. So think about when you use a k nearest neighbor algorithm, you will have to define the k values, but you will also need to define what will be the most appropriate distance metrics to be used. So that's that's it for the k-nearest neighbor algorithm, but then there is another variant called the distance-weighted k-nearest neighbor algorithm. And the idea is that, do we really want to trust neighbor solution or neighbor samples that are actually way further or significantly further away from other solutions? So typically, in this example, you can see we have a k-nearest or 5 nearest samples, 2 red dots and 3 green squares. So the usual outcome of the 5 nearest neighbor algorithm will be that the blue cross actually belongs to the green square class. But we can definitely feel that it's not the right decision here, because the best solution will be potentially the red dots. And the idea is because we have these kind of clusters that are very close to the samples that we want to classify, and we have a second cluster of points that are significantly further. And so instead, what we can do is to use a distance-weighted k-nearest neighbor. The idea is we want to add more weight, or to consider more the solutions that are closer to the solution and a little bit the solutions that are further away. You can see, for instance, the thickness of the lines between the different samples here is different, and the further we are, the thinner is the line, so the less we want to trust the solution. And so the idea and the way the distance-weighted k-nearest neighbor algorithm works is simply by refining the k and then algorithm by assigning a weight that is called wi to each of the neighbor based on how close they are. So typically, the closer you are, the higher you or the sample will count in the vote, in the final vote, and the further is the sample, the less it will be taken into account. And then, in order to make the decision, we simply count the sum of the weights of all the classes, and the class with the larger weight will work. Again, because we have a distance-weighted k-nearest neighbor solution, we need to know how we will actually define the weights according to the distance. And in this case, any type of weight function that will favor samples that are closer to the sample we want to classify will work. So typically, a very simple inverse of the distance like this one will work, but we can also use Gaussian distribution like the one displayed in the picture here, because it will also favor solutions that are very close to the sample. Typically, if the distance to the sample is 0, you will have the maximum weight, and the further you move away from the samples, obviously because it's a distance, you cannot have negative value, so this part of the Gaussian distribution cannot happen. But if you have a sample that move away from the query sample, the weight will rapidly decrease, and it will so the sample will count less in the final votes. A couple of additional remarks for the distance-weighted k-nearest neighbor algorithm. The good thing with this algorithm is that actually the value of k plays a smaller role, because actually if you have a very large k value, this means that you will take into account a lot of samples, but in this case, if the samples are very far away, even if they are taking into account according to the k value, they will not count that much because they will be most likely very far away, and so it will usually don't greatly affect the classification. We also have a specific case here when we have the k value that is equal to n, the size of the training set. So if actually we consider all the solution in the training set when we want to do the classification. And in this case, we will call this a global method because it's kind of capturing all the data from the data set. While on the other hand, if k is smaller than n, then it's called a local method because it will only consider the samples that are around the samples that we want to classify, and so only local samples and not all the global samples. And finally, the distance-weighted k-nearest neighbor algorithm is usually a bit more robust on noisy training example, mainly because it will consider, like the k-nearest neighbor algorithm, more than just one samples, but it will also take into account the ones that are closest, so also ignoring samples that can be noisy but also further away, as we discussed in the previous points. So that's everything we had to cover for the k-nearest neighbor classifier. So a couple of points just to for the discussion, in the k-nearest neighbor algorithm, one of its strengths is that it's a very simple algorithm. It takes a couple of lines of code to implement, and it's yet a very powerful algorithm. It's actually quite difficult to beat this algorithm, even with very powerful machine learning techniques like deep neural network. But the issue is that when you will have very large data sets, the k-nearest neighbor algorithm can start to be very slow. And that's actually where neural network will start to kick in. It's because in order to learn powerful neural network, you will need a large data set. And so it's exactly here that k-nearest neighbor will start to be a bit less interesting, and neural network will start to be more advantageous. Also, something to take into account that I haven't mentioned, we have the size of the data set, but not only the size of the data set, but also the size of the samples. If you have very large feature set like images, like the raw pixel of images that you want to classify, computing distances between high resolution images can take a lot of time, even if it's just an Euclidean distance. And so also in this case, the k-nearest neighbor algorithm can be quite slow. Naturally, there are ways to speed up the search. So for instance, we can use KD trees or locally sensitive hash and so on, but still it will be at some point quite slow if your data set is very large. And this is definitely related to the course of the dimensionality that you already have seen last week in the introductory lecture, especially because in this case, the k-nearest neighbor algorithm will rely on a distance metric. And the issue is that if you increase the number of dimensions, you will first of all need more samples to uniformly cover all the space of the possible features, which might be difficult to have, and will naturally require you to have a larger data set. And so you will very quickly end into the issues of the large data set, and so a slow k-nearest neighbor algorithm. But also, if you have a lot of features, some of them might be irrelevant, and so you might actually be making your decision based on the wrong set of features, and the actual clusters or the actual nearby solution might be a further away or in a different solution. So this is an example of the curse of dimensionality that you have seen already last week. And one of the solutions in order to avoid this issue is to weight the different features differently. Typically when you use the distance-weighted k-nearest neighbor, or you can also use some feature selection or feature extraction in order to know which of the features are more informative and on which you need to actually focus more of the intention of the weighted k-nearest neighbor algorithm. Finally, so here we talk exclusively about classification, but if you have a regression task, we can also use a k-nearest neighbor for the regression. So typically what we can do some k-nearest neighbor regression, and that's relatively simple. We can simply compute the mean value of the k-nearest neighbors. So remember that in the case of regression, every sample is not assigned or attached or associated with a label, but rather with a value, which can be a float value typically, or real value. And so here the idea is that now that we have a k different instances, we can simply compute the average or the mean value of the different samples, and that will lead, for instance, to this kind of samples. Similarly to the distance-weighted extension of the k-nearest neighbor classifier, we can use a locally weighted regression algorithm. The idea is that we will use weights provided by the distance-weighted k-nearest neighbor algorithm, but for regression. And by doing this, we will simply compute a weighted average or weighted mean across all the k value, but again by taking into account the weight computed by the weight function that I described previously. And that will, as you can see on this figure here, you can see that we will have a way smoother trends than the very ashy prediction here in the k-nearest neighbor regression algorithm. So that's it for the second part of this lecture, and the next clip will talk about the decision tree, which is the second biggest part of this lecture today. So see you soon.